got home from work and they were like, we just need you to like go out in the go lot and check over the next 2 days and just see if there's a key. I was like, what do you mean? They're like, well, Tucker Bell wanted 8 4-wheeler key. What about the 4-wheeler? 8 fucking 4-wheeler.
Now it's just
So now any one of my goats.
it's great. Is this somebody's factory?
How's your puppy, Mr. Thompson?
He's good. He enjoyed puppy playtime yesterday a lot. A golden doodle showed up who was much bigger than him, but would have known it with my corgi's attitude.
Really?
He's a small dog, big dog attitude. Small dog body, big dog attitude.
We had a 6-month-old corgi come here to the car yesterday. He's so freaking.
What? My parents want me to study the baby animals. So he's bad.
He's bad.
I don't think he's bad. Like, not to be like, so she on years ago, like, she doesn't really get anything. She just does her tours. Like, he eats everything. Oh, is she as big? Not really.
How big did she get?
Probably like 10,000 Lindsay. I don't know. I feel like she's just, like, she's not growing, which, like, she is, like, I see her every day. Yeah. Like, she's, like, the same size as Mallory's puppy, and he's, like, 4 months.
Guys got these 2 warm-up problems to get started with here today. Hope we're all doing well today. we've got a
Mr. Kaufman?
Yes, ma'am.
Abigail Beth doesn't need to find out.
Yes, ma'am. We have a considerable amount due today. It is very likely that we don't get it all done today, and that we may have to pick up on Monday with what doesn't get completed today.
So, like, one of the groupings was 59 to 65 for either wrong.
Yeah.
But it's 59 to 63.
Yeah, that's my fault.
Okay, do you want us to do the 65 on the 5th?
We did all that.
Okay.
Practice, practice is what's good.
I just want them to do the village.
Yeah. That's what I would do. Yeah, we have an absolute crap ton to do with this lesson. I'm not sure if we're going to get it all done. I don't believe I got it all done in one stint last year. So we'll see. We'll see. Because that happened a couple of times where one with, I know we did second derivative over 2 days. They did it over 2 days as well. Of course, I believe that I did related rates and optimization over 2 days, and we got those done in one. So we'll have to see how that shakes out here today. I am prepared for us to pick it up next week if we need to. As well as if we finish it all today, awesome. I haven't laid out your timeline for next week, but I will tell you this unit is relatively short. It's only going to be 5 sections. We're only going 4-1 through 4-5 here. Only going 4-1 through 4-5. I do believe, right now I actually think I only have 1 quiz slated for you all, but we'll see how that goes. We'll see how it all shakes out by the end of next week. It also depends on how far we get today, because your first quiz will be sections 4-1, 4-2, and 4-3. So that will kind of depend on where we finish today and what we end up doing on Monday next week before I can tell you when your next quiz will be. But I can tell you definitively it will be sometime next week. And by this time next week, we should most likely be finished with this unit and moving on to the test and study guide. So unit 4 probably will be the first test grade for next grading period. I don't know if the quiz will go on there, but I know definitely the test will go on next grading period. I know without a doubt the test will go on next grading period, but this quiz might be here, it might be there. I have yet to figure that one out. Okay, let's go ahead. Let's talk our warm-up problems here. Let's go ahead and let's talk our warm-up problems here. Definitely need my calculator here today. My keyboard. Get my markers. Who would like to help us with one of our warm-up problems? Callie, go ahead, miss. Do the first one. What did you do with the first one, miss?
I started out and I combined the 3x minus 5 and x plus 2.
And you combine these by doing what?
Multiply 2.
You just multiply them together. What do we get?
I got 3x squared plus 6x minus 5x minus 10.
Let's just go to the final quadratic.
3x
We should know how to factor.
x minus
3x squared plus x and minus 10, yes? I think this is absolutely the right track to go because it's going to be much easier to do each of these integrals separately rather than trying to do a product rule, which I haven't taught you yet. Questions? Okay. Callie, we do each one individually, yes?
10. Yes.
Okay. Now we're just looking for the antiderivative here. We don't have enough information to go the entire way, right? So capital Fx. What's going to happen here with our first one?
It's going to become 3x over 3, which simplifies x cubed.
We'll simplify in a second.
Okay. And then x squared over 2. And then minus 10x plus 6.
Yeah, I recommend getting them all written out and then going back and simplifying, not trying to simplify one term all the way, one step at a time. Do the antiderivative of each thing, then simplify each term. That way you're staying on the same thought process at the same step. Antiderivative, 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 simplify, simplify, simplify. I think that works a lot easier. Of course, that's my brain. My brain is not everybody's brain. Probably a good thing that it's not. We'll simplify. Of course, those 3's will cancel. Anything else cancel?
No.
No? Okay, so we'll leave it as x cubed. We can either leave that as x squared over 2 or 1/2 x squared if you like. And everything else the same. Questions here for our first one. Pretty straightforward, pretty easy, right? These can vary, and there's not really a good indicator about the overall difficulty of doing an integral, doing the antiderivative. There's not really a great indicator about that. We're actually going to take a little break from these here today. We're going to take a little break here from these today. And we're going to start setting up what we actually use integrals for. And for that, we're going to need to go back to limits and sums today. Limits and sums today. Who would like to help us out with the second part here, the second one? Colin, what do you got here, bud? What'd you do first? Wrote out our integral. Okay, so we're going to take the integral of what?
4x cubed plus 5x minus 2.
with respect to dx, right? Okay, so let's go ahead, let's do the antiderivative then. What do we have here?
4x to the fourth over 4 plus 5x squared over 2 minus 2x plus 6.
Very good, that's our antiderivative. Of course, we can do a little simplifying right here, right? And drop those 4's and just make that x to the 4th, agreed? Okay, what are we going to do from here?
Set the equation equal to 4 and plug it to 0 for x.
Yeah, we're given a point here. We know that the y value is going to be 4, right? We know the x's are 0. There's 0 to the 4th, 5, 0 squared over 2, 2, 0, and c. What does that make c, sir? 4. Okay. So what's my final answer, Colin?
X to the 4th plus 5 to 2 x squared minus 2x plus 6.
This is our actual equation here. This is our actual fx. That's given. Our actual y, right? Questions here for this one or concerns for this one? Okay, that knocks out our 2 warm-up problems. Did we have any homework questions we wanted to talk about? I totally forgot to ask for homework questions. Do we have any that we'd like to talk about or go over or discuss?
23 and 27.
23 and 27 from homework.
And then 60.
Yes, let's start with number 23. We have the integral. We have the cubic root of x squared dx. First thing we're going to do is rewrite this as a fractional exponent as x to the 2/3 dx. We're going to go ahead, we're going to add 1 onto that exponent, which means, of course, that's going to be 5/3. And that'll also become our new divider here for our antiderivative. Of course, plus c. And then we're just going to reduce that. 3 is going to come up. 5 is going to come down. We're going to flip that fraction. We're going to have the cubic root of x to the 5th. Questions here? Okay. Number 27 is very similar to the one we did yesterday in class. Very similar to the one we did yesterday in class. We have x plus 6 over root x dx. Let's go ahead. I'll do it like I did yesterday. I'm going to bring this up as x to the negative 1/2 dx. I'm going to distribute it in. This is going to give us x to the 1/2 plus 6x to the negative 1/2 dx. We can do each of these individually. This will become x to the 3/2 divided by 3/2 plus 6 times x to the 1/2 divided by 1/2. Of course, plus c. I'll flip this fraction to thirds, and that's going to be square root of x cubed. And then I'll flip this fraction. That's going to give me 12, and that's going to be square root x plus c. Questions here for 27. And what was the last one, Callie, that you wanted there?
67.
Number 63.
3.
Number 63 is like the very last one we did. Yesterday. We have some differential equations here. We have a second derivative is x to the negative 3. F's second derivative is x to the negative 3/2, if I'm reading that correctly. We have f to the first derivative is equal to 2 for 4. And then we have the first is 0, 0, so the origin in our original. So what we need to do is we need to do a first derivative, or not first derivative, an integral followed by a second integral. We'll do the first one here. This is going to give us an anti-first derivative. Let's see here, we're going to add 1 onto that, so this is going to become x to the negative 1/2. Of course, divided by negative 1/2, of course, plus c. This gives us negative 2 over square root x. The bottom fraction will flip, becoming a standard multiply by 2. And of course, this one with its negative exponent is actually going to go underneath. So this is what we're looking at here. We're going to plug in our point here. We're going to set this equal to 2, and I'm going to plug in my 4 and make this c. So this gives us 2, and negative 2 divided by 2 plus c. That gives us 2 equal to negative 1 plus c. That makes c 3. So my actual first derivative function is going to be right here. I'm actually going to take this, a variant here of this one here. I'm going to take this as negative 2x to the negative 1/2 plus 3. I'm going to kind of unstack it just a little bit, just so that way it makes it a little easier when I go to do my next integral. We're going to have negative 2x to the negative 1/2 plus 3 dx. This one, of course, the negative 2 is going to become my multiplier, so I'll multiply that in a second. I'm going to add 1 to that, so that's going to become positive 1/2 x to the 1/2. And this is going to become 3x and plus c. This is our antiderivative of the original function. This is going to become negative 4 square root x plus 3x plus c. And what we're going to do here for this one is, of course, evaluate at 0. So this is going to be 0, 0, 0, 0. So c is 0. Questions here? Okay, so that makes my original function then negative 4 square root x plus 3x. There is no constant at the end. Questions here? Okay, let's go ahead. Let's move on to what we need to do today, unless anybody online has a question. Doesn't seem like it. Okay, so let's jump into what we're going to do today. Today we are going to talk about area underneath a curve function. That is the goal today. That's the only thing we're talking about today, except for there's like a bunch of different ways we can do that. Here's your homework on slide 2, your homework, so that way I don't forget. Let's go ahead on to slide 3. Let's start with some notes here. So we're going to talk about the area of a plane region. Area of the plane region. So what we're going to do is we're going to estimate the area underneath a curve. And to do this, we are going to use a whole bunch of rectangles. A whole bunch of rectangles. If we had more time, I would also show you how you could do this with trapezoids, which is way better than rectangles. But I don't have that time. So, very simply, I'm going to have a curved graph, and I'm going to ask you how much area is between the curved graph and the x-axis. How much area do we have there? So there's a number of ways that we can do this, and a number of ways we can draw our rectangles. We have a right-handed sum, which means that we will do the area of the rectangles based on the right side of these respective endpoints for any interval I give you. So if I tell you we're going to go between, let's say, the x values of 0 and 4, and I want to use 8 rectangles, that would mean a rectangle every 0.5, correct? So instead of using the x value of 0 for my first rectangle's height, I'll use the x value of 0.5 for it. I'm going to draw a little picture up here just so that way we can kind of have a good idea of what we're talking about. So if I draw this nice curved graph here, let's stick with okay. So if I say I want to do between 0 and 4, and we're going to go 8 rectangles, and I'm going to do a right-handed sum, that means that every 0.5 we should have a rectangle. And what we're going to do is we're going to go off of this value, 0.5, to draw the height, rather than going off of the left side, which would be f of 0, to draw the height. Meaning that this one would come up at 1. This one will come up at 1.5. Meaning this one will come up at 2, 2.5, 3, 3.5, and of course at 4. And these would be our rectangles. Now when we fill this in, we have all this red area. So we have a little bit over here. We're going to have a little bit under in these sections. You see how I don't actually get the whole part there, right? So this is why we are saying we are using this to estimate the area underneath the curve. Does that make sense to everyone? Okay, the next thing is with a left-handed sum. With a left-handed sum, which is the same idea, but just flipped. Instead of starting at 0.5 for this one, instead of starting at 0.5, I'll start at 0 and draw it over this way. And then I'll do the same thing. I'll start at 0.5, draw it over 1. This one from 1 over to 0.5. Using the left side of the rectangle to set the y value. Does that make sense to everyone? Because if we're drawing in these rectangles, we're going to have two x values on the bottom. The left side 1, the right side 1. That's why we call it left-handed sum and right-handed sum, depending on which one we are using to set the height. Is that clear? Colin?
Is that the same curve you used for the right-hand sum above?
I tried to draw the same one, yes.
Can you put the right-hand side over the left-hand so I can see it?
I will try my best, sir, but you know art is not my specialty. Okay, so here's 0.5, right? So right hand is up here, it comes over. Right hand comes up here, it goes over. Right hand is going to come up here and go over. You see slight difference now. Okay? Questions here. Okay? Now things are going to get extra interesting because we have two more. We have the lower sum. We have the lower sum, which is when we find the height using the lower of the two endpoints. So I look at both values and I figure out which one is lower, and I use that one each time to draw my rectangle. Meaning that at no point in time will I have a rectangle over my graph, meaning that this will be an underestimation of the area. Does that make sense? Rather than having them bounce sometimes up and down above and hoping that it balances out, this is strictly keeping everything below the graph, allowing us to strictly work with an underestimation. There's plenty of times where this is what we would normally do, One of my favorite calculus problems to talk about with this is when we fill up tanks of fuel underneath gas stations. This is a really good example of how calculus is used to do that. The computer system monitoring all that always makes an underestimation because you don't want to overfill the tank. You would rather underfill it, right? You can always come back sooner, right, if you need to. Of course, there is many situations where the opposite is just as useful, where if we have a little bit more than what we needed, that's okay too. It all depends on the situation at hand. Calculus in the real world, if you will. Questions here. So that's how a lower sum works, and an upper sum works in the exact idea, but the opposite. Instead of everything being strictly underneath the graph, we're going to look at everything strictly being over top the graph by a little bit, an overestimation of everything. Are we okay with these so far? We have left-hand sum, we have right-hand sum, where we're strictly using the left points, strictly using the right points. We have a lower sum, which is always going off of the lower of the two y values, and a higher sum always going off of the higher of the two y values. I will tell you outright, part of what is going to make us possibly not make our time frame today is the simple amount of math you have to do, the simple amount of grinding of equations we are going to do today. So hope that we're all ready to work. There is one more we should talk about. The midpoint option. The midpoint option, which instead of going off of either the left or right, we're going to go from the center of the rectangle out. So instead of going from 0.5 or 0, I would split the difference and go from 0.25, hit here, and then go out to build my rectangle. Same thing over here. I go up from 1.25 and go out and split my rectangle. I go from here at 0.75 to go up and split my rectangle. Questions? Concerns? Sounds fun, doesn't it? I'm excited. Well, I'm only excited because Mr. Cotton has to try his best to draw a lot today. And you all know that I am not good at it. So we're going to work on Mr. Kaufman's art skills today. I should have asked Mr. Allison to come up. Are you all ready to actually try one of these? The concept here is not super difficult, I think, to understand. I'll tell you how many rectangles we want to do. I'll tell you the interval we're going to do it in. We want these to be evenly distributed. So we want these rectangles to be the same shape, the same size underneath. So we don't want, 3 that are small and then one real big one. We're going to try to avoid that if we can. There are going to be a handful of times where we might bring in something other than a rectangle. If we have like a nice perfect circle, for example, we might try to use a circle formula, but that's pretty rare that we have something like that. Okay? Just wait till we start doing these with limits and sums. So let's use 4 rectangles to approximate the area lying between y equal to negative x squared plus 5 and the x-axis. So we've moved on to slide 1, 2, 3, 4 now. So on to slide 4, we have our first problem. Y equal to negative x squared plus 5. And we're going to go between 0 and 2 using the right endpoints of the equation. So rather than giving you an outright, this is the procedure you should follow, I think it's best to do it while we do a problem. So I'll lead us through this one, but I'm going to have you guys help me just a little bit here. So the first thing we're going to tell you is a graph is super helpful here. A graph is super helpful. So that's what I'm going to do first, is I'm going to graph my function. I don't need a fancy calculator to do this. I know that this is just going to be a standard parabola that has been shifted up 5 and flipped upside down. I know that it will have a 0 somewhere over here on the other side of 2. Where that is specifically, we don't really care because we're not going to that 0, we're going to 2. So after this point, it doesn't really need to be that specific. I will tell you that you do want to make sure that at 2, you are, of course, at 1. And you do want to make sure that you're at 1. We should be right here at about 4. So I should redraw this here just a little bit better. 1, we want to be at 4. Terrible. Try again, Mr. Kaufman. Terrible. Try again, Mr. Kaufman. We'll get there eventually, gang. Don't worry. Maybe. Hopefully. That's not too bad. Third time's the charm. So you definitely want to check those endpoints. You definitely want those to be as correct as you need them to be. When you have nice clean points on your interval, you definitely want them to get them right. I want 4 rectangles here, which means what are the x values we're going to be concerned with? Not just 1 and 2, but what other ones are we going to concern ourselves with? How should we split up this interval? Every half, right? So let's fill those in 1/2 and 1 and 1/2. If you want to use decimals, that's fine. I'll probably use fractions myself. Okay, I want to use right endpoints here. So what are the x values that we're going to use? What are the x values we're going to use to draw my rectangles? Go ahead, Colin. 1/2. What else? 1. 3/2 and 2. We're going to go off of these right here. So this is what we're looking at here. So we're looking at the x values. If we're thinking about this like an xy tree, right? We're thinking 1/2, 1, 3/2, and 2 as our x values of choice. Yes? Okay. We need area. We need area. Right? That's what we want. We want the total area here of each of these, right? How should we set up a little equation to do this? I want the total area. So shouldn't we find each little area individually, right? Okay, so each little area, they all have the same width, correct? We made sure that they're all consistent across the bottom. So we do know that each one, when we look at length times width for this, right? That all of the widths here are going to be 1/2, right? Plus 1/2, plus 1/2, plus 1/2. What we need here is we need the length or height, if you will. So I'm actually going to swap that around and make this W times H, W times heights, right? Because that's more descriptive of what we're dealing with, right? How will I find the height? What's that going to be?
Plug in your x value.
That's going to be the evaluate, that's the y values, right? So this is going to be f of 1/2. This is going to be f of 1. This is going to be f of 3/2 and f of 2. Now you see why I went ahead and wrote a little xy tree here, right? Now, if you're paying attention, you might notice that there's a little bit of an easy way, faster way to do some of this. Go ahead and find the y values here. Go ahead and plug them in, grind them out. You have the equation up there, the negative x squared plus 5. Go ahead and plug them in, grind them out. You already have 2 of them. Hope they're all doing well on chat here. Hope we're all doing well on chat. Right now, it only looks like I got half of our A day in there. So I guess they're just going to get marked absent for today. Need some Y values here. Who's got a Y value for me? Y would be what? 4 point. I'm going to go 4 3/4. I'm going to go 4.75. Okay. What about at 3/2? 2.75. Very good. Okay, I will let you in on a little secret. Okay, let's go to Desmos real quick. Let's go to Desmos real quick, and let's graph this in Desmos. So when I type in my equation, negative x squared and plus 5. I typed something wrong there. Oh, I put 22. X squared plus 5. Okay, so when you go to Desmos and you plug this in, if you go up here to the little settings gear, right on the left side, and you click that, you see that you have some different options. The first one is to select a table. If you choose that table, it will bring up the XY table. And you can actually ask Desmos to grind some Y values for you. For example, down here where the table ends, you can add a Y value, say like 0.5, and we'll throw up the Y value for you. Or you could put in like 3/2, which would be 1.5, and it'll put the Y value up there for you. So you can use this to help you speed this up a little bit. I don't want you spending forever plugging in X's and getting Y's. This ain't math 1, okay? So this would be a great way. I know that you're going to use Desmos to graph your function. You're not going to draw it by hand like I did. I don't imagine you to. So I recommend that you use this to help you, okay? Let's go back to our slides here. So we have our Y values. Before I plug them in and start multiplying and adding, I'm going to do something to make this easier. When I look at this, I see a GCF. I see everything has 1/2. So I'm going to rewrite this as 1/2 times the Y value plus the Y value plus the Y value plus the Y value. That will make this a whole lot easier to finish out. So we'll have 1/2 times 4.75 plus 4 plus 2.75 plus 1. This gives us 1/2 times 5, 9.75, 12.5. And that's what I've done on our slides here. Questions about this? Okay, doesn't seem all that difficult. I really hope it isn't that difficult for you. But I will tell you that at different points, people do struggle just because there's a lot of moving parts. This is one of the higher concepts we're doing in calculus, especially when we start doing limits and summation with this. So it can get rather complicated. There's a lot of moving mental parts, if you will, as opposed to like the first derivative test, second derivative test, grind it down, get those numbers, plug them in, right? It's very straightforward, this, then that, then this. This one, there's a lot of fluid parts. Let's move on to our next slide. Why don't you guys go ahead and try this one on your own. I want 5 rectangles between -2 and 3. I have a new equation, y equal x squared plus 2. So we're going on to the next slide here. We're looking at example 2. Should be slide 6, 5. Slide 5. Let's go ahead and let's try this one out. This is where we're halfway through class and we've done one problem. This is why I said it's pretty unlikely we're going to finish all this today, as I got 20-something slides to get through, and we are only currently on slide 5. Great. Question, or just want to confirm what we're doing?
What like the amount of work you want, because like, plugging in the equation and do the table, shows them like every single step that I need. Now, find the answer.
I just want to see you write out the different steps that we need, like write out those half values that you're going to. Okay?
Alright.
And I like pictures. I should see a picture. I should see a table of some kind. I want to see you write out the actual addition and multiplication that you're doing to some degree. Okay?
Because I was like, this doesn't seem like enough work.
They're going to feel pretty quick at first, and trust me, you're going to want to come back to this if we end up reaching the limits today. But that's essentially what an integral is. To cut to the chase, is an integral is doing infinitely numbered amounts of rectangles. As a derivative is the infinite amount of slopes as we get closer and closer and closer. An integral is the infinite amount of rectangles being added together. What limit would that infinite amount of rectangles approach? That would be the area, and that's what an integral is. It's a limit of a summation. Whereas a derivative is a limit of slopes. Let's go ahead, let's try this one out here. Let's try this one out here. Okay. First, let's get a graph drawn here. We got x squared plus 2. 1, 2. We got our nice parabola. 1, 2, 3, 5. Did not draw a very good graph this time at all. Bad job, Mr. Kaufman. 1, 2. Okay, so at 1, we're going to be at, all right, excuse me, at -1, we're going to be at 3. And at 2, we're going to be at 4. No. 6, 3, 6 up here. And then 3 is like all the way up there because Mr. Kaufman did a very poor job of drawing this one out. And still did even worse. Off to a great start with the pictures, gang. I had a good first one. It was fun while it lasted. Okay, we want 5 rectangles between here, right? So this actually works out pretty nicely because I gave you 5 x values to fall between, right? So what's the width of each one going to need to be here? 1, a full 1, right? Okay. Now where are we doing these off of? What x values will we be using to draw our rectangles? -2, -1, 0, 1, 2. So if I'm using a left-handed sum, I'm going to go with the start at the left part of the interval. If I'm using a right-handed sum, you kind of want to start at the right-handed interval and work backwards. Okay? Well, we have all these, right? -2 is 6, right? Yeah. -1 is 3, 0 is of course 2, 1 is also 3, and 2 is also 6, right? So we have a nice clean parabola. It's on the x-axis. We have that mirror image allowed, right? This is something, this symmetry is something that you can actually use to help speed this up a little bit. Because rather than doing all 5, you could get away with doing like 2.5 here. Especially if you have like 3 on each side of the axis, then you don't necessarily have to do both sets if it's a true mirror image. Nonetheless, here when we set up our total area, each one of these are being multiplied by 1, right? When we look at this, f -2, 1 times f -1, correct? So we could do the same thing last time we pulled out a GCF, but since they're all being multiplied by 1, that's not really necessary here. We can simply sum our y values together, correct? So if we sum those up, we've got 6, 3, 2, 3, and 6, 12, another 18. We're looking at 21. Did I do that right? 20. Mr. Kaufman can't math. What's the wonder why they even let me in this class? Questions here. And you can see that's our work here on the slide. First thing I do is I draw in, I bring in our green square, which is going to be the directions on how I attack the problem. Draw the graph. And our rectangles underneath as described. I forgot to draw the rectangles. Find the area of each one, which we did, and then total them up. Okay, let's try another one. Let's move on to the next slide. Slide 6. Wish we were on slide 7. Go ahead and try this one out. We're going to do midpoint intervals here. 5 rectangles going from the midpoint intervals. No, it's not. No, it's not, but I tried really hard. How we feeling? Let's go ahead, let's attack this one here. Let's go ahead, let's attack this one here. What x values we're going to be using this time? 0.5, right? So 0.5, 1, 0.5, 2, 0.5, 3, 0.5, 4.5. So starting right here, going up, and then out on each side, right? And then right here, going up, and then out on each side. And then right here, going up, out on each side, here, out each side, and here. So we end up with something that looks like this here. Questions? Far. What's our y values that we're interested in? What y values we're going to get?
24.75,
Go ahead, Jake. What else?
22.75, 18.75, 12.75, 4.75.
Now, when we set up our area part of this, right? They all have the same width, correct? They all have the same width. That width here is, of course, 1, right? So we could set it up in the same way that we set up the last one, where we can just sum that column together, right? So what is our total area looking like here? 33.75?
83.
I was about to say 33 is too low. 83.75 sounds good to me. Questions here? Concerns here? Okay? Let's do one of the other two as well, and then hopefully we'll be able to start a little bit higher level here. Go ahead and let's tackle this one. I want you to use lower sum intervals for this one. 3 subintervals, -1 to 2. And give us just 2 or 3 minutes to do this one. We need to kind of pick up the pace here a bit. When we set up this XY table, what all do we need to start checking? What X values do we need to check? How will this one work? Let's do this one together, because this one can be a little bit trickier. What X values do we want to put in here? 0
And 1.
and 1. I'm going to plug in 2 just to be safe. Okay? So I'm going to plug in -1, 0, 1, and 2. Those are the X values that we are concerned about here. Those are my possible points along my interval for us to have 3 clean rectangles, right? Okay, so at -1, we have a Y value of 2. At 0, we have a Y value of 1. At 1, we have a Y value of 2. And at 2, we have a Y value of 5. Are we all okay? All right, so when I look at this first rectangle, we're going to go off the lower 2. We're going to go off of the lowest 1. The lowest 1 here for my first rectangle is at 0. So I'm going to go off of that one to draw my first rectangle. When I look at the next rectangle, I'm going to go off the lower one as well, which is, of course, still 0. And then when I look at the last one, I'm going to look at my 2 Y values. Which one's lower? This one. So this is where we're going to draw that in. These are the 3 rectangles we are looking at here. Questions here? Concerns here? Colin? We're pairing them up like this right here. Is rectangle 1. Right here is rectangle 2. And right here is rectangle 3. So out of these 2, which one's lowest? Out of these 2, which one's lowest? And out of these 2, which one's lowest? That can mess people up. Questions here? This would be relatively easy then to do. These have all, of course, a width of 1, right? So this is going to be 1 square unit plus 1 square unit plus 2 square units. So we're looking at a total area here of 4. Questions here? So when we look at this one, the instructions look a little bit more complicated there in my green box. When we draw this graph, it's best to find the lowest Y values first. So I draw the graph, of course, and then I start doing the X, Y tree. I plug in all the possible X values I could use to do this, to set the bounds of my rectangles. Why don't you try the next one here? Actually, you know what? Yeah, go ahead, try the next one here. Do this next one. So we're looking at slide 8 now. We're at slide 8. Go ahead and try this one out.
You want me to kill it?
Yes, kill it, I'll step on it, hold on.
It's inside, outside it's so lit, but I have it out.
It's so sad. It's not like your pet one.
I know, but I do have a pet one.
All right, what are we using here? What x values are we going to be concerned about here? We want to use right-handed endpoints. What are our endpoints going to be then? I want 6 rectangles. How am I going to get it? What width do we need to go? Pardon?
0.5.
We need to go 0.5. We have a distance here of 3, right? 5 minus 2 gives us 3. We want 6 rectangles out of those 3, so we're going to have to go every 0.5. So we're looking at right here, here, and here being additional points for us. So we're looking at 2.5. That's my first right-handed endpoint. I'm looking at 3 as my next one, then 3.5, then 4, then 4.5, then 5. 1, 2, 3, 4, 5, 6. What y values are we looking at here?
9,
9,
14, 20, 27,
Now, when we look at the total area here, this is back to that very first one where each of these only has a width of 1/2 for its respective x value, right?
Wait, why did you start at 2.5 and not 2?
Because we're starting out a right-handed sum. 2 would be a left-handed sum. So I'm going to factor that 1/2 out, and then I'll sum up all the fx's that I have. So 1/2 plus, or 1/2 times 9 plus 14 plus 20 plus 27 plus 35 plus 44. This is how I would approach it. I'm not going to multiply each one by 1/2. I'll do one multiplication, one addition, right? Make it a little easier. What did we get?
Final answer,
Yes, sir.
74.5.
Jake says a 74.5. Let's see what Mr. Kaufman has. I guess it doesn't have my answer up there, but it is in fact 74.5, Jake. I guess I somehow forgot to put it in. Okay, so what do we do when I give you this type of problem, but instead of saying I want 6 rectangles, what are you going to do if I ask you for 600 rectangles? Cry? That's not going to be an option. I mean, it's always an option. You always can cry. I'm not going to tell you not to, but Mr. Kaufman wouldn't want to make you cry. Calculus does that on its own. No, we're going to resort to other techniques that are going to work better for something along that line. We're going to go to using our summation formulas. Using this for a large number of rectangles becomes very, very cumbersome, very tedious. It's a lot of plugging in and grinding. That's what slowed us down here for the first 40 minutes, is plugging in and grinding. Which, like I said, this ain't Math 1. So we're not going to be doing this very often where we're going to do it by hand. Instead, we're going to rewrite these area formulas as summation formulas. That's what I'm trying to get you to see here by factoring out this 1/2, is that this can be rewritten as a summation formula. We have an equation. We're going to be going up incrementally, right? You remember way back in Unit 1 when we talked about summations a little bit? When we talked about limits? Yes? Okay. So we're going to be bringing those back here again. So what we're going to do here is going to rewrite these area formulas so that way they are summations. So we're going to say, okay, we're going to go from starting at this point, incrementally up by 0.5 into this equation. We're going to add up the results, right? So a question like this would look similar to, say, a summation problem. We're going to have n start at 2.5. And we'll go to 5. We might have to stress here that we're going up by 0.5, but you get the idea. Then in here we have our 2x squared minus x minus 1.
This has it as x equals 2. You have it as 2.5.
Well, yes, because I probably want to do this for this few rectangles. But you'll see what we're talking about. But yes, using this last one as the example, this is how we would kind of approach it. We shouldn't have set x to start on a decimal. Honestly, that's what we should. We should refrain from doing that. We should go with between 2 solid endpoint to solid endpoint. You can, it just doesn't always work very nicely. You kind of need to specify that your increments there are going to be by 1/2. Okay. Questions here? Okay, so let's just remind ourselves about some summation stuff before I just assume that we remember everything flawlessly from Unit 1. Because I bet if I put a summation problem up here, we're going to have no idea how to do it. Do we remember any of the formulas from summations from you? Cool. Great. Awesome. This is definitely not going to take 2 days then, for sure. Okay. Let's start with some easy ones here. Okay. Let's start with number 1. What is number 1 asking you to do? The sum of what numbers for number 1? 1 through 6, right? So it should be 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? What does that come out to be? What is 1 plus 2 plus 3 plus 4 plus 5 plus 6?
21.
Pardon?
21.
He says it's 21. Is it 21?
23.
Okay, we got 2 different answers now. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10.
21.
It's 21.
Okay, yeah.
Okay? I wonder if there's a way for us to find that outright. Wonder if there's a way that we can use some type of equation there to skip to that rather than having to physically add them together. Because right now, this isn't really saving us any time. We're still going to have to find each one, right? So that's what we're going to build towards is some quick hit formulas to help us with these summations. Help us add some stuff up here. What about our next one? What is that going to ask us for? What are we going to add up there?
5 plus 1, 5 times.
Nope.
0 plus 1, 1,
0 plus 1 plus 1 plus 1 plus 2 plus 1. It's going to end up with the same result, isn't it? It's going to start with the same result, end with the same result, I should say, but it's not the exact same starting formula. So it is possible for 2 different equations to spit out the same sums if they're starting at different points. What about the last one? What's the last one going to spit out? What are we going to sum up there? What are we looking for? What plus what plus what plus what?
9 plus 16.
9 plus 16 plus 25 plus 36 and 49. The perfect squares from 3 to 7, right? Okay, here's some basic. Well, I originally gave 4, but I decided to throw a 5th one in there. These are some basic sums to help you out. So going back to the previous problem, going back to some of the previous one, if I have a constant in there, and I'm just adding that constant X amount of times, then it would just be the constant times X. Or that's what we have there for our very first rule. If I have just a number there, if I'm just taking the sum of 4, not the sum of 4x or the sum of x, just the sum of a number, it's that number however many times I want to sum it together. Is that okay? If I take the sum of just a singular x, take the sum of a singular x, what that will be is the number of x's we're going to go through times that number plus 1 on the top, and we will cut it in half. So this is the very first example I gave on the previous slide. This is number 1 from the previous slide. When I'm looking at this, that would be 6 times 7 all over 2. 6 times 6 plus 1 over 2. 6 times 7 gives us 42. 42 divided by 2 is 21. And wasn't that the answer to the first example? Back on slide, what slide number was that? I forgot. I say it was slide 10. Yeah, slide 10. The one below it is a nice standard x squared. Nice standard x squared. It operates very similar to the one above it. I think you should understand how the two will be related, as one is just another I factored in, another x factored in. And then I've even gone as far as to say x to the third power below there, or of course I to the third power. And the last one I gave you is the geometric formula, the geometric sum formula. The geometric sum formula. This works best for exponentials, where you have some base and x is your exponent. This also can work really, really well if you have x in the denominator of your fraction. If we have like a rational equation to start with, rather than a quadratic or cubic. If I start with a rational equation where you have maybe x plus 4 on the bottom, you can also use this there as well, although it is a little bit trickier. I'm not sure if we'll look at those problems or not if we're going to have time in this unit. I don't want to overwhelm us with integration out the gate. We have time to go back to it. Know these formulas and know them well. You will want to be able to reference them quickly. You will not want to have to dig through your notes to know them. Are we all set here? Okay. I have a few more for us. These ones are truly the base ones. If I look at this example here, I'll show this as we wait for everybody to finish copying that. If I wanted to rewrite this equation, which was 2x squared minus x minus 1, I would rewrite this as the sum to, let's say that we're going to do it, let's say, what do we say, 6 times 4, right? So I would say, starting at 2 going through 5, times the sum of x squared starting at 2 going through 5, minus the sum of x starting at 2 going through 5, minus the sum of 1 starting at 2 going through 5. This is how we would break this up. Questions? There are some other techniques that we can apply and some other things that we can do. Just wait till we put a limit outside of this and say as n goes to infinite. Here's 2 more for us. I think that these 2 can be helpful. Let's see what we can do here with these. When we look at our first one here, we have a fraction, 1 over n, k squared plus 1. This is what this would build out for us, yes? 1 over n, k squared plus 1. So when you look at that, as I expand that out, right, towards whatever n is going to be, right? If I say it's 10, it's 10. If I say it's 50, it's 50, right? As we build this out towards 50, what's something that you notice about each one of these every single time? You see the constant multiplier out in the front, 1 over n. N's not changing. K is what's going to increase. N is just a constant. What you can do is you can actually factor that constant away and multiply it at the end. So when I did this one just a second ago, instead of doing all the sums of 2, I can take that sum of x squared and just multiply it by 2 at the end if I would rather do that, which is what I would highly encourage you do. When you look at the next example with number 5, you see the same deal. I have a constant multiplier out in front. The first one, number 4, on, this is what, slide 12, right? Yeah, on slide 12, we have a constant multiplier on the top of the fraction, a constant divider, I guess if you will. And number 5, we have a constant multiplier. We can factor those away so long as they are remaining constant. They cannot increase with our function. They have to be a consistent. Just like I factored out 1/2 when we did the areas, we can factor out this before we do the sum. Are we okay here when I look at 4 and 5? When I look at 4 and 5. Okay. Let's evaluate this for n equal to 10. I will lead us through this one. So going on to our next slide, slide 13. By the way, I know I don't draw these e's right. They're not e's, first off. They're epsilons. They're sigmas, actually, is what I believe they're called. So we have I equal to 1, so we're going to begin at 1. We are going to go to 10. And we have our formula of I plus 1 over n squared. Okay, so something I'm going to do first here, something that we can do first here is we can factor some different things away. We can manipulate some different things away. So the first thing I'm going to do is I'm going to factor out 1 over n squared. I'm going to remove a 1 over n squared from this set. So that's going to go outside my entire summation. Are we okay with this so far? Because n is really just 10, right? So it's a constant, so I'm going to leave it out there on its own. If you want, you can swap that right now for 10 or even 100 if you'd like. 1 over 100 right now if you'd like. What I'm going to do here is I'm going to separate this into 2 different sums now. I'm going to take my 1 over 100, and I have my sum of, that's terrible, what is that? Of I plus the sum, oh, good Lord, I told you I can't draw this worth anything. I give up. This is what we're going to be looking at from here. Are we okay with these first 2 steps? We're all comfortable here. I saw what could be a constant multiplier or constant divider, so I factored it out. I removed it from the sum to make that easy. Then I see that the sum is really kind of 2 parts there, I and plus 1, so I'm going to treat each one as its individual sum. Okay, my next step is to use the given formulas that I have here. So, who wants to help me with the formulas? Who wrote them down? I know Callie did because she asked us to wait for a minute. Callie, can you give me the formulas here? Let's give the formula for I. What is this going to become? It's going to become what? What is this going to become? What do we swap I for?
It's under the formula.
It's in the formula. Back to your notes. Basic formula right here. I.
Okay.
We have that as n times n plus 1 over 2, right? What's this one going to come out to be? This is a constant, right? So plus our constant, which is 1 times n. So we have 1n. Are we okay with this? This is part of the reason why I don't substitute that n in right away. Because if I leave it as n squared until here, then I can plug all the n's in at one time. That is the advantage to waiting to do that. So now that I've done it, now we can just plug it in. This is going to be 1 over 100. This is 10 times 11 over 2 plus 10. Okay? 1 over 100. That's going to be 110 divided by 2 is 55 plus 10. So we're looking at 65 over 100 or 0.65.
Wait, where did we get 1 times 10?
From our constant of 1.
Yeah.
It's the constant times the number that we're going. The number we're going here is 10. So 1 times 10 is 10. Questions? Now, of course, you can just express this as an equation. That is also fair for me to ask. That's actually what I did over there. That's actually what I did for mine, is I sent the 1 over n squared through and then just simplified down. But you can, of course, plug n actually in as well. I was kind of trying to kill two birds with one stone here because I know I'm running low on time. I can't even see the clock right now. Oh, we're out of time. We out of time. So I guess that's going to be it. I guess we're definitely going to have to finish 4.2 on Monday. So see if you can start some of your homework. See if you can start some of it. You won't be able to do all of it, but we are out of time, gang. So let's pack up quickly, as Mr. Kaufman barely finished that problem on time. I don't mind going slower through this lesson because this is how integrals work. This is kind of the understanding behind them, just like we did derivatives and slope. So I want us to make sure we really understand what's going on at a foundational level. So as we start looking at more complicated integrals, we can always remind ourselves, where did we start? We started with the integral. All right, guys, I will see you later. Sorry for running so late to the post bell. Have a good weekend. Hold on, you give me 1 second.
Are you starting mine at the bottom?
I thought I did just now.
Anna
Did I not?
and Carolyn, report to sign out, please.